Hello! Today we're gonna dive into the topic of large language models playing poker. I will build a case for why LLMs are just a perfect fit for it. We should probably forget about all the other attempts to solve poker. You'll see. Actually, one of the reasons I started creating YouTube videos is that I would create this one. Poker used to be a huge part of my life, and I could talk for hours about game theory and solving this wonderful game called Texas Hold'em. And now I have to squish it all into 12 minutes or so. One thing, I'm not gonna show you how different LLMs compare in poker or shove a bunch of poker hands into one LLM. No. That is not what I do here. We're gonna go deep. First topic, perfect versus imperfect information games. So a perfect information game would be chess. It means both the game state and opponent's moves are visible, meaning in any given chess position, there's at least one best move. If you find again in that position, there's no need to change anything, you can just play the same best move. In game theory, it is known as a pure strategy Nash equilibrium. Nash equilibrium, by the way, in a very simplified manner, is a situation where you cannot gain any additional advantage by changing your strategy, given every other player does the same. Actually, the only reason we have so many openings in chess is because we didn't fully solve chess. We know there's a pure strategy best move, likely one in the beginning. We just don't know what it is. So how do we find that best move? Well, in any chess position, you'll have to do a lot of perfect calculations in addition to strategy, which LLMs are not well suited to do. But in imperfect information games, there's either a game state or opponent's move they are not known, and thus pure strategy might not always work. Sometimes it does work, for example, like in Prisoner's Dilemma, but not always. Easiest example to explain is rock, paper, scissors. So opponent's move is not known, thus in order to play optimally, you need to randomize between 3 different actions. You have to play rock, paper, scissors, 1/3 each. This is also known in game theory as a mixed strategy Nash equilibrium. So we're finally in poker. Opponent's moves are known, but the game state is hidden. You don't know what are the cards in the deck or your opponent's hands. And again, the optimal Nash equilibrium strategy will be mixed, like this. This is what the strategy looks like for one of the nodes in the poker game tree. There's of course thousands of these, since there's multiple betting rounds, different actions from players, different cards on board, and so on. And for each combination, we would get a different version of this table, where every square is a different set of cards in your hand. This table is a bit simplified, compressed. There's actually more combination of cards than shown here. Bottom left notes unsuited cards, different color. Up right, same color cards, or suited. So in this particular situation, this is pre-flop, you would have to fold all the blue hands and play the others. So let's say you have Queen-Jack suited. And in this situation, in order to play optimally, you have to go all in 62% of the time, raise 10%, and call 28%. And like in rock, paper, scissors, you must mix. Again, that's a mixed strategy Nash equilibrium. By the way, in the poker world, it is usually known as GTO poker, game theory optimal. You can see right away that all of this is pretty fuzzy and probabilistic. You know what else is fuzzy and probabilistic? Large language models. These guys are trained on the whole internet, which includes many situations where there's a need to make a prediction based on incomplete or ambiguous information, exactly the same as in poker. Even more, the last layer of every LLM is just a probability distribution of the next token, meaning they are stochastic in nature. By the way, every time you say stochastic, your perceived arrogance level goes over 9,000, so you hear this the last time from me. You can just say random, right? Anyway, this random nature makes large language models pretty unpredictable themselves. And unpredictability, that's extremely beneficial in poker world. Next point. I had a video, link in the description, where I've built a case for why large language models are horrible at chess. The main crux of it They are bad at forming two-dimensional abstractions. By the way, I'm not saying neural networks or transformer architecture are not able to form two-dimensional abstractions. They absolutely can. But it's just not something current LLMs are built to do. While in poker, of course, there's no need for 2D. I had this demo in my chess video where I try blindfolded chess and just completely fail. But in poker, I don't even need a blindfold. That's obvious, right? You can close your eyes and reason about any poker hand with 100% precision. There's no need for two-dimensional abstractions at all. Poker is a game of mind where, there's a hidden information and you have to read other players, and that matters the most, more than any visual cues possible. And that actually fits large language models perfectly. Next point. So you may ask me, oh, but why bother with LLMs and poker? Isn't poker solved? But you just showed us the image of a Nash equilibrium strategy. It's here, right? Just learn it. Well, yes and no. This situation was solved and this image produced using a search algorithm known as CFR, counterfactual regret minimization. And that one is pretty resource intensive, and we only have enough resources, it seems, to solve two-player situations. If you add more players to the board and naturally expand the game tree, well, compute time for CFR rises exponentially, and we can no longer calculate what the Nash equilibrium strategy is. Meanwhile, LLMs are, of course, not constrained by any of it. But slight note here. If you want to train a neural network to play poker, LLM or not, you're likely gonna rely on CFR to do the evaluations for your actions, and then you will be constrained. But unless you do self-play, maybe we'll come back to this later. There's more. I saved my best point for last. So all the Nash equilibrium stuff, it holds if we assume everyone is playing the same strategy, a perfect game. But poker, that's of course famous for the fact that everyone can play it. And not all the players can play the optimal strategy. And in fact, no human player can memorize exactly that. That's impossible. It's too hard. But in regular poker games, there's many different players who could just be playing bad or too aggressive or too tight or whatever else. We're certainly not playing anything close to Nash equilibrium. So let's say you play poker versus someone who doesn't play the optimal strategy. What should you do? Well, now you must deviate from Nash equilibrium in order to better exploit that other player. You're already exploiting him with Nash equilibrium, just not good enough. So in rock, paper, scissors example, if you meet a player who's a paper guy, he just always plays paper no matter what. Well, if you keep to Nash equilibrium and play one thread of each and randomize, you won't lose, right? But you won't win either. In order to win, you need to deviate and play scissors all the time. In the poker world, this is known as exploitative poker. You need to adapt to different players' personalities you play against. And in computational poker, we don't have a search algorithm exactly which could take into account players' personalities. No way. Well, unless you are a large language model. These are trained on natural language data, which often includes human emotions, behaviors, and all the contexts. This makes LLMs uniquely capable of understanding and adjusting to players' tendencies, which traditional poker bots cannot do at all. All right, it's time to play an actual poker hand and show you how good LLMs can be and what limitations can we have. Just to preface, I played a ton of hands versus GPT-4o mostly, and it has beaten my expectations, really. The analysis it makes for common quizzes is pretty solid and often spot on. But I wanted to show you a different example. Not because it's a clear case, it's not. But these situations are what make or break any good poker player. So the hand goes like this. This is actually a live game from Hustler Casino. It's a deep cash game. You're in the hijack with 4 free hearts, UTG +1 races, and you free bet. I know it's a bit opportunistic, but in a deep cash game you can get away with this. And then a small blind 4 bets. And you call. Flop comes 8-4 king. Small blind bets. And you call. turn is 9. Small blind bets again. You call again. River is a 10. And small blind bets, kind of small. So what do? Well, let's ask GPT-4o. GPT-4o gives back quite a detailed and mostly spot-on analysis. We're really interested in the river decision, of course. Well, with a bottom pair and opponent betting all rounds, we almost never ahead, right? Most sensible action here is to fold. But wait, we did not tell him all the information. We know about our opponent. He's a fishy TikTok influencer. What about now? Oh, he says dynamics of a hand change significantly. Again, quite spot-on analysis, and now GPT-4o expands the range of our opponent with hands like ace-jack and ace-queen, and now suggests to raise instead of folding. And that's actually pretty aggressive and valid play. I'm impressed. By the way, if you want to know what happened in the actual hand, well, the hero, hijack, Norwegian chess player, called. Also a possible decision, and GPT-4o would say it's reasonable. The TikTok influencer showed ace-jack. I also wanted to show you one interesting thing. Since I prompted this hand multiple times, here's one of the answers I got. And it's a bit weird. GPT-4o suggests bluff raising, again, the same thing. This is fine, but it also says the opponent might fold hands like ace-queen. This is weird, since ace-queen is a worse hand, we don't need it to fold. So he doesn't seem to know basic poker hand rankings, namely that the bottom pair beats ace-high. And after a big back and forth, he voices it explicitly. Ace-high beats a pair. That's just wrong, right? But also when, you see, I just repeated what he said without trying to contradict him, GPT-4 kind of realized the mistake on its own, which means it's an important thing. It means that there's no fundamental problem. Mistakes like these, they can be corrected with some minimum chain of thought, and I prompted O1 Preview several times with the same thing, and O1 Preview never made such a mistake. So again, given this hand is pretty fuzzy, LLM seems to really have a grasp of what's happening here and can adjust to different player personalities. Alright, so why is no one really researching this? Well, of course, with ethical issues regarding gambling, but still, that's such an amazing game. There used to be this computerpokercompetition.org, no longer alive. There's actually quite a lot of attempts to train neural networks held by CFR, the same search algorithm, but not LLMs. Well, except this paper, PokerGPT. They achieved some results with a tiny LLM, 1.3 billion parameter, which we fine-tuned on hands played by actual people. And they were able to achieve quite okay results. It got maybe as good as regular people, but I feel the benchmarking process, that was somewhat lacking. They evaluated it versus Slumbot, which is CFR itself, and also AlphaHold'em, which is self-play neural network. Very interesting, but still, these bots can only play two-player mode, and meaning these evaluation results are a bit synthetic. There's nothing about player personalities, there's also no multiplayer pods, so there's plenty of work ahead. Research needs to be done, we likely need self-play and reinforcement learning, LLM poker arenas need to be created, and I'm sure in the following years we'll have AI, likely LLM, capable of beating the best human players in real-life situations. Stay tuned.